lengthy one, enhancement of catalyst performance. That's basically what it is by doping. So, Shakir, you have 8 minutes to make your presentation, and your time starts now. Over to Shakir. Shakir, Shakir, can you hear us? Shakir, please join the meeting.
Hello, can you hear me, sir?
Yeah, now we can hear you.
Actually, there's a problem with my mic, so maybe
Yeah, it's fine now, I suppose.
can you hear my? Can you see my presentation?
We can see your presentations too.
Okay, sir. So I'm just starting it now.
Yeah, you can start now.
Thank you. Yeah. Good morning, all of you. This is MD Shakir. I'm doing chemical engineering from Curtin University, and it's a joint collaborative PhD of IIT Ahmedabad and Curtin University. So my topic today, which I am going to represent, it's enhancement of catalyst performing by doping of boron over nickel cobalt and nickel cobalt bimetallic catalyst over ceria zirconia mixed oxide for dry reforming reaction. So these are the presentation outlines. So mainly, 1 minute. Yeah. So mainly, why we are doing dry reforming of methane reaction, because it is the best way to utilize greenhouse gases like CO2 and CH4 towards the valuable gas feed like syngas. So once we prepare syngas, then we can easily prepare any hydrocarbons any fossil fuels by the help of Fischer-Tropsch reactions. And so with this work, we are just using nickel cobalt based catalyst over the support ceria zirconia mixed oxide with the dispersion of boron. So mainly the main work is to attempt to reduce the catalyst during the preparation by the using of sodium borohydride and then we'll study its impact for the reaction for the dry reforming of methane reaction. And also the part of work is to evaluate the deactivation of the catalyst, which is like major problem for dry reforming of methane reaction. So these are the reactions involved for dry reforming. The first reaction is main reaction, dry reforming of methane reaction. The second one is reverse water shift reaction, and the third one is methane decomposition reaction, and fourth one is Maillard reaction. So this is the catalyst preparation part, in which I have used the nickel nitrate and cobalt nitrate and added ceria zirconia mixed oxide, and used NaBH4 reduction method. So added NaBH4 like on the basis of 3% of boron, and then washed it, filtered it, and then dried in a vacuum oven, and then ready to prepare, ready to use it for dry reforming reaction. These are the results. So first we evaluate the reduction of the catalyst by using H2TPR. So here we can see like by the addition of NaBH4 in the catalyst, so there was a reduction of the catalyst, but not like 100%. There is some consumption of hydrogen during the H2TPR, but for a bimetallic catalyst, it is lesser compared to like monometallic catalyst, especially for nickel and cobalt. Here is like we did ICP for evaluating the concentration of nickel, cobalt, and boron. So it's, as we added 15%, so it's around 15% with the ratio. Like we have prepared 5 types of catalysts. Like the first one is 100% nickel, the second one is 75% nickel, 25% cobalt, third one is 50-50, fourth one is 25-75, and last one is 100 cobalt. So accordingly, we got the concentration and also the boron concentration. Like we have added 3%, so it's almost 3%, but not exactly. Here from TPR, we found the degree of reduction. So as I told you, like there was not 100% reduction takes place. So there was like 29%, 23%, 21%, 24%, 33%. Here also we can see like there's a lesser for bimetallic catalyst compared to monometallic catalyst. These are the XRD of the catalyst in which we can clearly see the peaks of support mixed seria zirconia oxide, and also the nickel cobalt for all catalysts, 100%, 75%, 50%. These are the reaction conditions. That's not good, but so in which the reaction temperature is 600 degrees centigrade and pressure is 1 atmospheric pressure, and the feed ratio of the flow feed gases are 1:1:3, like CH4, CO2, and N2, and we are analyzing the product by the using of GC. Here's the result I got from my reaction studies. So we have performed all catalysts, and also we have compared it with the non-boron catalyst with like the catalyst which we have not used NaBH4. So here we can see like with NaBH4 treated catalyst, there is a less decline compared to without NaBH4 treated catalyst, and also the like bimetallic catalyst have more conversion, not CH4 here, like CO2 conversion, and CO2 conversion, we can see like bimetallic catalyst performing more performance was more good compared to monometallic catalyst. But here also the decline in conversion is higher compared to non-boron catalyst. Also in production of syngas, so in production of syngas, like around we got 0.7. Also we compared it with the non-boron catalyst and other bimetallic catalyst, we can see like there's a less decline. After that, we have like analyzed the spent catalyst by elemental analyzer. So the deposition of carbon over the catalyst means over the boron containing catalyst was higher compared to non-boron catalyst. Also, like for bimetallic catalyst, the deposition of carbon was very lesser compared to like other catalyst. So here, just I am concluding my work. Like reducibility of the catalyst shows the reduction of the synthesis, like catalyst used by NaBH4. NaBH4 was higher, especially for bimetallic catalyst. The TPR shows a high reduction were observed for 75%, like 3:1 ratio of bimetallic catalyst. XRD, from XRD, we got the metallic peaks of nickel, cobalt, and zirconia. The main thing is like with boron catalyst, we have achieved like there's a good dispersion of nickel and good dispersion of boron, and also we got the more activity and maximum conversion we observed for 75% to 25% catalyst, and mainly the carbon deposition was very less compared to non-boron catalyst, and especially for like bimetallic catalyst 3:1 ratio. Thank you. Any questions, please?
Thank you, Shakir. I'm sure that audience may be having some questions. Any questions from the audience? No, Shakir, one thing that I noticed is that the carbon deposition on your catalyst is too high. How do you circumvent this problem?
No, sir, it's a bit low compared to like traditional.
13% is not very low.
No, sir, 13% is non-boron catalyst, which I just compared the catalyst which I'm representing. It's like boron based catalyst, so it is like 4.89%. In traditional catalyst, it's like 13.56 catalyst. So yes.
So your method is an improvement that way.
Yes, sir, with the addition.
You actually were talking about methane conversion. Methane is converted to what?
Methane and CO2 is converting to syngas like H2 and CO.
H2 and CO. So that's an excellent
Yes, sir.
fuel. Very good. Yeah,
Yes,
nice
sir.
piece of work. Thanks for participating. Thanks for presentation. And thanks for sticking on to the time. Good luck to you,
Thank
Shakir.
you. Thank you so much, sir, for your compliments. Thank you.
Okay, Niti Ravindran. Niti
Yes, sir.
Ravindran, can you please join us now?
Hello, sir.
Are you ready to join us?
Hello, sir. Am I audible? Yes,
You are
sir.
audible. You are audible. Am I audible? Can you
Yes,
join
sir.
us
Yes,
now?
sir. Audible.
Can you join us now?
Yes, sir. Ready.
Yeah. You start.
Yes, sir.
You can start now. Upload your talk and start your presentation.
Okay, sir. Sir, are the slides visible?
Yeah, sure. Nice. Full screen.
Yes. Okay. Yes, sir. So, a very good afternoon, one and all. As part of MatCon 2021, I'm going to present my work entitled as FOTCNQ doped benzodiazepine based P-type polymer, unraveling the doping mechanism and thermoelectric parameters. I'm a PhD student and I work under Dr. C. Vijayakumar at CSIR and IST Trivandrum. So before moving on to the topic, I would like to give a brief introduction about what thermoelectric effect is. So thermoelectric effect is the direct conversion of heat into electricity or electricity into heat through two related mechanisms, that is the Seebeck effect and the Peltier effect. Seebeck effect is the temperature difference between two dissimilar electrical conductors or semiconductors that produces a voltage difference between two substances. And the reverse is the Peltier effect, where the electrical current flowing through the junction of the connecting the materials will emit or absorb heat as described in the figure. So energy from various sources like thermal power plants, nuclear power plants, then waste incinerators, automobile industries, and waste hot water released from industries, etc. contribute to the primary energy. And about 66% of this primary energy is lost as waste heat, and that can be efficiently retrieved to electrical energy with the help of thermoelectric materials. So some of the major advantages of thermoelectric materials are it releases no pollution into the environment, it has no moving parts, maintenance, it's less maintenance fee, and it is compact, lightweight, it can be used in zero gravity environment, it does not have any noise, it have long lifespan, non-toxic, scalable, and it lowers the production cost. However, some of the disadvantages include lower energy conversion efficiency rate, slower technology progression, and lack of customer as well as industry education about the thermoelectric generators. A typical thermoelectric module is consisting of legs of alternating P and N type material that are connected electrically in series and thermally in parallel. And the quantitative measurement is based on the Seebeck coefficient, that is alpha is V by delta T, and the power factor, which is PF, is alpha square sigma, where sigma is the electrical conductivity, given combinedly giving the dimensionless figure of merit, that is alpha square sigma T by K, where T is the operational temperature. We can also express in terms of thermoelectric efficiency denoted by eta. And how to select a good thermoelectric material? In order to maximize the CT here, in order to maximize the CT, we have to minimize the thermal conductivity. So in that aspect, semiconductors are appropriate candidates where we have a moderate electrical conductivity, which can be improved by heavy doping, and a high Seebeck coefficient, and also a low thermal conductivity. So among the organic and the inorganic semiconductors, the reason for choosing organic semiconductors is its potential abundancy, low intrinsic thermal conductivity, as mentioned before, high flexibility and solution processability, and its low cost. So with this insight, we are coming to our work where we have used the semiconductor PBDTT EFT, which is a conjugated push-pull polymer based on benzodiazepine based donor and thienothiophene acceptor, and it is doped by a strong acceptor that is tetrafluorotetracyanoquinodimethane, that is FOTCNQ. The energy levels of the polymer and the dopant are in such a way that the efficient electron transfer from the HOMO of the polymer to the LUMO of the dopant is feasible. And basic mechanism of doping includes two ways. That is, one is the ion pair formation, that is electron transfer from HOMO to the LUMO of the dopant. Whereas one more mechanism is possible in otherwise cases, that is the charge transfer complex formation, where the frontier molecular orbitals of the polymer and the dopant hybridize to form a new set of orbitals, that is the empty as occupied as well as empty orbitals. And coming into our UV visible NIR spectra, upon doping, we can see that the strong pi to pi star transition decreases in intensity, and the new absorptions in the NIR region is visible, or it is increasing with increasing dopant concentration. This is corresponding to the polaronic absorption that is caused due to the interaction between the polymer as well as the dopant. And the polaronic absorptions P1 and P2 are can be seen here. And we can see in there is no anion absorption corresponding to the F40C and Q dopant at the 800 nanometer region. So we assume that the mechanism of doping is via the charge transfer complex formation or the CPX formation. Further, the Raman spectra of the pristine sample is compared with that of a known polymer, that is P3HT, which is known to have dope with the ion pair formation. We can see that the Raman shift is, of the C triple bond N is much higher in the case of P3HT than in the case of our polymer, where a formal charge of less than 1 electron is transferred. So in that case also, we assume that our mechanism of charge transfer is via the CPX formation. Further, high resolution peaks of carbon 1s, fluorine 1s, and sulfur 2p peaks are analyzed. And we can see that a slight shift in towards a lower binding energy region is observed in all the three cases. That is confirming the p-type doping as well as the Fermi level shifting towards the HOMO of the polymer. And further, the UPS spectra was also studied, where the work function of the pristine polymer is at 3.81 electron volt, and upon increasing the dopant concentration, it is increased to 4.59 electron volt. So this increase in work function also confirms that the doping is shifting the Fermi energy level to the HOMO. And this is further confirmed by the Fermi energy spectra, that is upon doping, we can see the shift decrease from 0.59 electron volt, that is E HOMO minus E Fermi, is shifting from 0.59 electron volt to 0.27 electron volt. And we have formulated this band energy diagram with the work function as well as the Fermi energy values. And coming into the thermoelectric parameters, the electrical conductivity is drastically increasing from 10 weight percentage of dopant to 20 weight percentage of dopant, and a maximum of 0.09 Siemens per centimeter at 20 weight percentage of dopant is observed. And on further increase of the dopant concentration, we can see the dopant is not contributing anymore, and the electrical conductivity is decreasing. And the p-type doping is confirmed by the positive Sieber coefficient values, and upon increasing dopant concentration, we can see that the Sieber coefficient decreases, that is from 645 to 542, leading to a maximum power factor of 37.4 at 20 weight percentage of dopant. And we have also fabricated a flexible device of the PBDT TFT with 20 weight percentage of dopant using polyimide sheet with the fabricated TEG showing an output power of 0.025 nanowatt at a delta T of 63 Kelvin between the hot side and the cold side, with a maximum output voltage of 0.16 millivolt and a load resistance of 1 kilo ohm. And coming to the F40C and Q doped polymer blends, a major challenge faced is their de-doping. So as we have compared in the Raman spectra with the P3HT system, here we can see that upon increasing the temperature, that is at a moderate temperature itself from 60 degree to 90 degree, P3HT F40C and Q system shows a rapid decrease in the anionic absorption as well as the polaronic absorption in the NIR region. So this decrease is due to the thermal instability of such systems, and the thermal stability is another major factor that governs the functionality of a thermoelectric system, since we deal with the temperature application over the compound. So In our proposed system, we can see that at a moderate range from 60 degree to 90 degree, the de-doping does not occur, or it is not visible from the optical signatures. So the stability of the dopant that is existing as a radical anion in the system is playing a crucial role in thermally induced degradation observed in FOTCNQ doped P3HT films at even moderate temperatures. In conclusion, we demonstrated the existence of charge transfer states in FOTCNQ doped PBDTT EFT, achieving a high Seeber coefficient in high electrical conductivity, particularly for PBDTT EFT in solution processing, is rarely reported. And the charge transfer complex state leading to a high conductivity of 0.09 Siemens per centimeter is a benchmark value, and thermal de-doping of FOTCNQ can be neglected by proper selection of polymers, and this is relevant while choosing materials for real-time study of thermoelectric devices, as it deals with always an exposure to ambient atmosphere and also elevated temperatures. Finally, acknowledgement. I would like to thank my guide, Dr. Vijay Kumar C, Director CSIR and NIST, and organizers MatCon 2021 and CSIR for financial support. Thank you.
Okay, that was a really nice presentation, Nidhi. And I'm sure that
Thank you, sir.
there will be some questions from the audience. No questions from the audience. If there are no questions from the audience, I may be forced to ask questions. Couple of questions, actually. Can you tell us something about the material selection?
Yes, sir.
Yeah, why did you select these two materials? You used, one dopant and one polymer. What was the motivation behind selecting this particular polymer and this particular dopant?
Yes, here this FOTCNQ dopant is a strong acceptor having 4 fluorine atoms. It is well known to have a good charge transfer properties with the polymer. And coming to the other polymers like thiophene-based P3HT or PBTTT, etc., is already well studied and saturated, and donor acceptor type polymers are not really explode in the field of thermoelectrics. So in that aspect, one thing, and also due to the stability of the BDT core, that it is more stable. That is the reason for choosing this polymer.
What I was wondering is, since you already have a dopant, what's the point in taking a donor acceptor sort of polymer? Isn't it okay if you're taking simply a donor polymer? Or is it that you want some sort of an electron shuttle between these two? Once an electron is removed from this, the radical cation which has been formed, that has to be stabilized by electron.
What I guess is the radical anion forming is more stable in the case of such polymers.
Radical anion is formed for the acceptor, isn't it? Yes. For the polymer, it is a radical cation which is generated.
Cation.
So yes, there may be some sort of a shuttling mechanism there whereby the radical cation is stabilized. With all these compounds, I think the major problem is formation of reactive intermediates like radical cations and radical anions, which probably will be resulting in slow destruction of all these organic materials. And another thing which I noticed is, okay, once you go for the equation, it's wonderful. You said that the thermal conductivity has to be low, so we have to go for a semiconductor, the kappa factor.
Yes.
But at the same time, if T is high, then the efficiency is much higher. Isn't it?
Yes, so operational temperature, yes.
Yeah, operation temperature. And for the sort of material that you are taking, there's a limit to the operation temperature that you can have, I suppose. If you go anything below, beyond say 100 degrees, that may be a problem. So basically you will be constrained to use this device in a low temperature situation, maybe somewhere between room temperature to 100 degrees centigrade, which of course is not bad, but supposing that, you want to generate some energy from a thermal device like a internal combustion engine, where so much of heat is generated, this type of material may not be useful. So what I wanted to know is, this is not a question, this is just for my information, because I am a novice here, I don't know much about it. Are there inorganic materials which have been used for the same purpose?
Yes, sir. Bismuth telluride and other sort of materials, antimony telluride, etc. has been used, and they are stable up to 800 degrees Celsius.
They can definitely use at a higher temperature.
Yes, but again, their factors are their thermal conductivity is really high. So we have to balance these two and maximize the seat.
What you gain in terms of T is lost in terms of kappa, isn't it?
Yes.
Okay. Yes. Okay, that was really nice.
Thank you.
Thanks for all the information that you provided. And
Thank you.
that's the end of your talk. Okay, you can now log out. Thank you very much.
Yes, sir. Thank you.
Yeah, basically there was one more oral presentation by Dr. Marilyn Milton. Seems that she hasn't joined. So the morning session, we are not having one person to present. So I think the morning session ends here. And it's time for me to sign off also. Before I sign off, let me thank the organizers of MatCon, especially Dr. Srikumar, the chairperson, and Naibin, who is the convener for this wonderful event, for giving me an opportunity to chair the longest session in MatCon 2021. Okay, I'm really thankful to all the people who presented the work here today, both the oral presentations as well as invited lectures. They all stuck to their time, gave a good piece of information about their latest research as well as the basic ideas which are behind the project that they have taken. So this was really nice, quite informative, and I'm sure that everybody will be benefited, highly benefited by attending these talks. So thanks everybody once again, and with this, I sign off. Thank you very much.
Thank you, Pradhaban sir, for chairing the session. We are dispersing here for lunch. The next session will start at 2 p.m. IST. All are requested to join the meeting before 2 p.m. Thank you.